welcome to the Explainer. Today, we're taking a fresh look at something we literally use every single day, the capacitor. Now, we might know what they do on a surface level, but trying to visualize their actual behavior in a time-varying system, yeah, that can quickly turn into a mess of dense calculus. So instead of getting totally bogged down in the math, we're going to jump into Dr. James Bales's lectures and re-examine capacitors and RC circuits through this absolutely brilliant, intuitive physical analogy. Let's get into it. Okay, so let's frame our entire understanding around this one incredibly helpful physical analogy. A capacitor is simply a bucket for charge. Honestly, this is the single most important concept to keep in your head today. Scratch the idea of invisible electrons moving through abstract fields for a second. Just picture a bucket. It stores something up, holds onto it, and then releases it exactly when the system needs it. It's elegant, it's super physical, and it just perfectly describes the component's underlying job. To really make this bucket analogy work for us, we kind of need to map our electrical terms over to a fluid system. Just imagine water flowing through a bunch of pipes. In this setup, voltage is the exact equivalent of pressure, right? It's the physical force pushing the water through the pipes. And current, that maps perfectly to the volumetric flow rate. It's basically asking, hey, how many gallons per second of water are moving past this specific point? By cementing this concept, we can easily see that a capacitor is really just an empty vessel. It's waiting to store a volume of electrical charge, filling out as that voltage pressure pushes the current right into it. All right, let's look at the basic math behind our bucket. Don't worry, it's beautifully simple. Q equals C times V. The total amount of charge, which is basically the total water in our bucket, or Q, is determined by multiplying the capacitance, C, which is the actual physical size of the bucket itself, by the voltage, V, which is that pressure pushing the charge in. So when current starts flowing in a circuit, it's really just the flow rate of charge filling up that specific bucket. And it'll keep flowing, filling it up, until the charge hits the total capacity that's dictated by the voltage pressure. You know what's really fascinating? It's how the visual language of electronics literally mirrors physical reality here. The universal schematic symbol for a capacitor is drawn as just two parallel lines separated by a gap. And this isn't some abstract design choice. It represents precisely what a capacitor actually is in the real world. Two pieces of conductive metal separated by air or some other insulating material. The charge just gathers on these parallel plates, separated by that physical gap. It's literally a direct snapshot of the component's physical architecture. Okay, so let's step away from a static component for a second and step into a time-varying system, an RC circuit, which is just a resistor and a capacitor combined. We really need to look at the exact chronological sequence of what happens the very moment a switch is flipped to let the current flow. Before we do anything, at time t less than 0, our bucket is completely empty, zero charge. Then, at exactly time t equals 0, boom, we instantly flip a switch to connect a battery. From there on out, for all time t greater than 0, the physics completely takes over. The charge starts filling the bucket, but it gets slower and slower as it fills, asymptotically approaching its maximum limit. Let's visualize this exact hardware setup. Imagine a switch in a circuit. It starts at position 1, where the capacitor is effectively grounded and totally empty. But the instant that switch jumps over to position 2, it connects to the voltage source. The pressure is on. Current rushes through the resistor, which by the way acts kind of like a narrowing in a water pipe, restricting the flow, and our electrical bucket begins to rapidly fill up with charge. And this brilliantly illustrates the dynamic reality of that whole filling process. When you first throw that switch, the bucket is completely empty. So the current, our water flow rate, is at its absolute maximum, just rushing in. But as the bucket fills, it actually starts to push back. This causes the voltage across the capacitor to shoot up rapidly at first, but then it gently levels off as it gets full. On the flip side, because the bucket is pushing back with its own pressure, the incoming current starts at its peak and just dies out exponentially to 0 once the bucket is totally full. Now let's move into some real-world applications here because physical buckets absolutely have physical limits. When you're picking out a real capacitor for a circuit, you have to check its specs. You've got the capacitance value, which is your bucket size. You have the maximum voltage, which is the maximum pressure that bucket can handle before it breaks. And this is vital. You must check if it is polarized or non-polarized. Polarized capacitors have a specific positive and negative lead. If you hook up a polarized capacitor backward in a circuit, the chemical reactions inside will fail catastrophically. Like it can actually heat up and literally blow up right on your workbench. No joke. And knowing that actually helps us understand another type of catastrophic failure, dielectric breakdown. Think about the dielectric material, the insulator, sitting right between those two metal plates. When a voltage is applied, an incredibly intense electric field pushes across that gap. Now, if you push the pressure too high, or if the manufacturer made the plates way too close together, that electric field becomes overwhelmingly strong. Eventually, a spark will literally jump across the gap, totally breaking the inflator. Your capacitor pops, short circuits, and the whole shebang is completely destroyed. So, we've covered some absolutely crucial fundamentals in this explainer today, but I want to leave you with a bit of a provocative thought to chew on. We now completely understand how our capacitor bucket fills up from a steady direct current stream. But what happens if the source isn't steady? What if we push the flow of charge back and forth rapidly, alternating directions, kind of like someone pushing a kid on a swing? If you push a swing at just the right speed, it glides perfectly. But if you try to push it back and forth 100 times a second, the swing barely moves at all. So how does changing the frequency completely rewrite the rules of the RC circuit we just learned? Well, that exact question unlocks the fascinating world of RC filters, and it completely changes how we manipulate signals. Think about that and keep exploring.